now that we have our tools in place, we know how to multiply vectors, and we have our nabla, so we know that we could take a dot product of two vectors and get a scalar. We know that we could take the cross product of two vectors and get a third vector that is perpendicular to the first two. And we know that if we take this very special thing and take a dot product with a vector, we get the divergence, or how quickly field lines spread apart. And if we take this version, the so-called curl, then we measure how much they are bent around, how much they curl and come back in place. So the first one are field lines that look like this, and the second are field lines that come back and close in. So one thing we didn't mention, but if you take just the parts that curl, as we would here, figure out how much they curl, and then we take the divergence of what's curling, we get 0. Every single time, guaranteed. That's actually one of the properties of the way this works out. So, what does that mean? Well, we have seen fields before that diverge, and we've seen fields that curl. Let's take a look at Maxwell's equations. So his first equation is that the divergence of the electric field, so how quickly the lines spread apart and leave the origin of your space, is equal to the charge density, so how tightly packed the charges are, divided by the electric permeability of free space. So how quickly electric fields radiate out depends solely on how tightly packed the charge is and how easily those field lines can penetrate the vacuum. That makes sense. You'll notice here that the right-hand side of the equation contains no position information. There's charge density, and there's a constant that describes the universe. So the fact that we're using position vectors in this nabla, but they don't show up as positions here, says that if Maxwell's equations hold, when we change reference frames in relativity, we must see matching changes in the electric field. Either that, or we're going to see a difference in the charge density. The second equation, when we're looking at the divergence of the magnetic field. Well, the magnetic field, we know, always comes in closed loops. You cannot have an isolated North Pole or an isolated South Pole. You must have both. And because every field line closes in on themselves, that's 0. Every time, every magnetic field. The third of the 4 Maxwell's equations, we have the curl of the electric field. So the electric field, if we have an electrostatic situation, just a point charge sitting there, there's no curl at all. It spreads out. But we also know if we have a charge that's accelerating, well, that's the charge that produces magnetic fields. It can release electromagnetic radiation. If we have a charge that's changing over time, then we might have some other changes going on. We've got some magnetic fields. So this actually comes out to how quickly the magnetic field changes over time. So if you have a uniform magnetic field, then the electric field does not curl. If your magnetic field changes, it's going to force changes in the electric field. Now, this is a connection that Maxwell put in because it fit with experiments. They couldn't really come up with a good reason why it was true. That will come, but it'll come with relativity. And then finally, we've seen the divergence of the electric and magnetic fields. We've seen the curl of the electric field. It makes sense that the next place we're going is going to be the curl of the magnetic field. And because magnetic fields are closed loops, we expect this to not be zero. It actually works out to being the magnetic permeability of free space, so how quick or how easily magnetic fields can penetrate a material, times the current density. So how much current is flowing shows up. Again, these terms were put in by experiment. And then here we have the mu naught epsilon naught times the time derivative, or how quickly the electric field changes with time. So we can see that Maxwell figured out from labs and from experiments that the electric and magnetic fields depend on each other, especially as they're changing in time. But these were just in here because they fit experiments. There was no really good reason to explain why not. We are finally going to get to that. So we're finally going back to that, what they call the thought experiment that introduced the whole thing. If we have two charged rods to an observer in the same frame of reference, they're going to repel because we've got like charges and no motion. Classically, to an observer that's moving, they would attract because that magnetic field can eventually overcome the electric field. Now that we've got Maxwell's equations, we'll be able to put some of this together. Because what we're seeing here is a divergence of the magnetic field that is zero no matter what. We've got an electric field that only depends on the changes in the magnetic field over time, not over position. We've got an electric field that diverges according to how densely charged or how densely packed the charges are. And we've got a magnetic field with a curl that is going to depend partly on current flow. We know that current produces magnetic fields, so makes sense that current flow would be in there, and on the change in the magnetic field. We can even look at this mu naught epsilon. Should be a subscript 0 on that one. But we can look at the mu naught epsilon naught. And remember, that is 1 over the speed of light squared, which can come into this equation a little bit as well. But these are the ideas. So in our next video, we're going to take a look at these solid rods and see what happens as they move through time and space.